So today is the second last lecture of the class, but it is the last in-person lecture of the class. And so here we're going to talk a little bit about deep neural networks. Now this is not a machine learning course, so if you do take the machine learning course, you'll probably learn more about deep neural networks. Has anyone taken the machine learning course in here? Okay, it's at the same third level, so I thought maybe some people have taken it. Is anyone currently taking it? No? Okay. I believe there's also like a statistics course that's specifically in deep learning, so if you're interested more in deep learning, you could probably take that course. But I just wanted to go over it briefly as an introduction so that you know sort of what it is, because it's so prevalent these days in whenever you talk about AI, most people are actually talking about something that's related to deep neural networks. And so I just want to give you that information as sort of a send-off. And then for the last lecture that I want you to watch independently is, here's a YouTube link. So Google and DeepMind put out the AlphaGo movie for free on their YouTube channel. And now I say for free like it's some sort of gift, but it's really just marketing for Google, right? But it is quite an interesting movie. Has anyone seen it yet? Okay, so it's really entertaining as far as like a sort of academic story goes. And what will happen is, now that you know heuristic search and you know a little bit about neural nets and deep learning, they use both in order to do the first version of AlphaGo. And so after you've learned a little bit about deep neural nets, then you can watch the AlphaGo movie and actually understand all the terminology that they're talking about. Now, it's not a lecture. It's an actual like produced like movie. It could be a feature film documentary. But it's like really entertaining. It's got a human story to it. It's understandable by anybody. Like if you didn't know anything about AI, you could still completely understand and appreciate the movie. But it's nice to know, oh wow, they're talking about this thing that I did in my assignment, right? So please watch that, because there will be a question about AlphaGo on the final. Now that question is not going to be like, what was the name of this person, or like in what city did they do this? It's going to be like an algorithmic or theoretical question about what they did, not like random details about who the producer was or something like that. So let's get into deep neural nets, and after I talk about that, I'm going to read the D2L post about the final exam, and then I'll just go over all the topics that we did since the midterm, and I'll go over possible exam questions and stuff like that. So, all right. So deep neural networks and deep learning. Deep learning is essentially learning that's done with deep neural networks. So if you're interested in learning more about this independently, then there is the Deep Learning book, which is available for free online, and this Dive into Deep Learning website, and there's many more. There are dozens of excellent resources on deep learning, many, many courses on YouTube. You could follow along. You could learn about TensorFlow or Torch or any like Keras, any of these libraries that you can use to deep learning, to do deep learning. We're not going to go into any like APIs or examples of how to program it. We're just going to go over the high-level theoretical details. So in essence, at the highest hand-wavy magic view of deep neural networks, they're just neural nets that have many hidden layers and extra processing. And I hope that you've all watched the lecture that I posted on neural networks, because if not, you might be a little bit lost with some of the stuff in this lecture. So they've been around since before 2012, but they became very popular in 2012 because Geoffrey Hinton released this paper that used deep neural nets for image classification and used a ton of GPUs and got really excellent results and really changed the shape of AI as we know it for the last decade. And so the rise of GPU computing power has made deep neural networks more feasible because you can do all sorts of floating point calculations in parallel using GPUs and tying a bunch of GPUs in together. As you saw from the neural net implementation video, if you watched it, there are many things about a neural net calculation which are completely parallelizable, right? You can do all of the dot products in parallel for a given layer. They don't depend on any other, calculations for that layer, and so because of that, you could just throw them on a GPU, which are really good at doing that specific thing. It's hilarious how like GPUs were made to do graphics processing, but it turns out they're also perfect for running neural nets through as well. And so deep neural nets combine multiple techniques, which sometimes you'll look at a deep neural net and it will have a specific architecture for a specific domain. So maybe over here we're trying to classify birds. Over here we're trying to learn about a state or a value network for a Go board. And so the deep neural net structure may vary a little bit depending on the particular implementation that you're doing. But what you'll see is there's a bunch of different features and Features and techniques that are used in deep neural nets, especially convolutional deep neural networks, that you can sort of plug and play to form your own structure for these neural networks. So they all share similar techniques, but they're not all exactly the same. You wouldn't just take one deep neural net and apply it to, or one deep neural net architecture and apply it to every possible problem. And so one thing that Geoffrey Hinton did was got a very, very good result at image classification. Okay? So this image classification problem set had been worked on for years as a sort of benchmark for how well AI was doing, especially in computer vision and image classification. And when Geoffrey Hinton's paper was released, they absolutely blew the socks off everybody that had come before it using deep neural networks. And this result was very surprising. And then a bunch of companies said, oh, wow, the more money you throw at this, the better results you get. We have money, right? And so then Google and Facebook and Microsoft and all these companies that had deep pockets started taking these techniques that were developed in academia and just like throwing huge amounts of processing power at them. And we have the state of the world that we're in today, where you can spend millions of dollars training a big neural network. So one of the key things one of the key techniques that are used in deep neural networks are called convolutions. Has anyone heard of a convolutional neural network or a CNN? A few people. So what a convolution is, and convolutions are key not only in neural networks, but in image processing in many parts of computer science. But I'm going to explain what a convolution is, so you'll know what it is, so then we can see how we can apply it in a deep neural network setting. So in a convolution, what we have is we have some input image. So typically, we're talking about this with respect to two-dimensional images. Okay, so whatever image data that we have. This is very, very popular in image processing and feature detection in images, so being able to track something in an image or detect what an image might be representing. But of course, they could be used in other domains as well. So you have some input image. So here in the middle, for example, is an input image. And then we're going to have some kernel. That is not a kernel. That's not a neuron. That's a kernel. Let me fix that real quick. Okay, so that's supposed to be area, not kernel. But anyway, that's fine. So we're going to have some area up here, for example, a 3x3 area like this. So it's just a 2D array or a matrix. And that's going to look at a 3x3 area of the input and produce a single output value based on that. And so whatever calculation is being done, we're looking at some area of the input image, doing a calculation on it, and then producing a single number from that. And that area is called a kernel, and then the next, I don't know why I'm saying neuron, but the next layer would look at, or sorry, the next iteration would look at a different area. So here it is in animated form, which makes it a bit easier to process, in my opinion. So here we have the input image down here. So this would be the input image. And then we have a kernel, in this example, of size 3x3. They could be of size 4x4, 5x5, whatever. Doesn't really matter. But here we're looking at a 3x3 kernel size. And then for each 3x3 area in the image, we do some calculation based on that, and we produce another image, which is the result of that calculation. Okay, so this is what we do. We take some area of the image, we iterate over each pixel in the image, apply that area around it, and then come up with a new image based on that. So here's an example of, like a numerical example of a convolution, where we have this input image, where we might have ones and zeros. So say this is like a black and white image, or it could be some other binary data, et cetera. And then what this is doing is the first 3x3 area is going to produce this value. The second 3x3 area is going to produce this value. The third 3x3 area is going to produce this value. And what we can see over here is in the kernel, what we're doing essentially is taking the top left value, multiplying it by 1, the middle top value, multiplying it by 0, the top right value, multiplying it by 1, and then summing all these things together. So the values inside the kernel are telling us what we're going to do with the values there to produce the next thing. Yep?
So can we go from the convolved feature back to the image in this case or in the general case?
No, because this is not a reversible calculation. There are many, many possible inputs that it could give you the number 4, right? So it's not a reversible calculation. But that idea we will come back to, but not in terms of convolutions. But a good question. So we take some input image, and we produce some smaller image that is the result of this convolution. And you're saying, OK, but what could this possibly be used for? What's an actual example of this? And one really good example of this is an edge detection kernel. So down here, what these kernels do is they detect change in an image. So what are edges, right? If you think about it, most of your vision, when you recognize features or shapes or humans or faces or objects or whatever, you could do the same thing if the image was in black and white, right? Or even not only grayscale, but literal just black and white. Because it's really the edges that make up shapes and objects and stuff. So when it comes to image processing and detecting features and objects and stuff like that in an image, most of the color information and most of the grayscale information really isn't a key step in determining what that object is, right? Now, of course, maybe you have some specific instance where like a red apple would be classified differently than a green apple, and so of course you would need color in those cases. But like for detecting someone's face or something like that, you'd probably only need the edges. So what we're doing here is we're using this kernel to say, okay, let's say we want to detect a horizontal edge, right? So here we would multiply values on one side maybe by a negative, values on the other side by a positive, and what this will give us is big values when we had like maybe dark values on one side of this line and light values on the other side of this line. So we can do this in the horizontal direction, we can do it in the vertical direction, we can do it in both. And so those changes in values that we detect are essentially the edges in the image. When it goes from one lightness color to another lightness color in a sort of a harsh change, then that is an edge in the image. So we would apply this kernel to the image in the way that we just saw, and the output image we would call the edge image. So for example, there's a very famous input image here in image processing, and we would run it through this kernel, and we would get this result over here. Now, this is not a perfect result. There are better ways, there are better kernels than this one. But you can see here that, yeah, we've got enough information here to basically be able to detect that this is a human face probably wearing a hat, right? And what convolutional neural nets are going to do is use this sort of kernel in order to pre-process the image to get it down into a simpler form so that neural nets can work with it a bit easier, right? Because what we want to do is get our input data in the most basic and important form possible without all the extraneous stuff that we don't necessarily need, right? The minor changes in color from your cheekbone down to your neck is not going to really impact the outcome of the classification, but it would possibly make the processing a lot more difficult if we weren't doing this initial convolution step. Did you have a question?
Yeah, I wanted you to repeat that. How is the minor changes ignored by this convolution algorithm?
Well, let me show you an example. Okay, so I have this right here. So here's another type of edge detection. And so what happens is essentially, when we do this, and one side of the, This is kind of annoying because it's moving back and forth. But you have very different values on one side and very different values on another side. And if those values are very different, then the output number that we get is much bigger, right? So the way that the kernel is constructed is that if on one side it's dark and one side it's light, then the output number is going to be bigger.
So do we have a threshold output number?
No, we're not talking that. Don't get too far ahead here.
No, I'm just
Yeah.
wondering that at what point can we say that is a big number?
That is completely dependent on the problem, and it's not an issue. Like, we're talking about theoretically how deep neural nets work, not exactly choosing thresholds and stuff like that. So what you do is you apply a kernel like this, and you get out these values. And so what this kind of looks like is that you take this kernel, you apply it to the whole image, and then you're essentially turning that input image into an edge-detected image. Okay? So you take this input image, which has a bunch of color information, and you produce this image. And if you think about it, from the purposes of like a self-driving car, other than the fact that like, oh, it would be nice if I could detect if their brake lights were on or whatever, this is pretty much all you need to detect a car, right? It's got the basic features of a car, and so that's the filtered image. And what we may do then is do several of these things, right? Maybe you'll have different edge detection features. Maybe you'll have different type of feature detections. But each of these kernels is going to run over the image and produce a new output image. And then what you get from this is called a convolutional layer. Okay? So what exactly these different layers are isn't super important. But now you kind of get the idea of we have one or more kernels, convolutional kernels, that are going to run over the image and produce some sort of feature space image that we're then going to run through our neural network. Okay? So if you look at this filtered image here running through this kernel, you can still see that, it would be, if I were to really want to do feature detection at this, what I would want to do is maybe turn up the contrast. So if you've ever done any image editing on your phone or in Photoshop or anything like that, the contrast is essentially the difference between the lights and the darks, right? And so there's a bunch of different algorithms that you can use for contrast enhancement and stuff like that. But basically, we want the lines to get a little bit brighter so that we know where the edges are a little bit more. So one of the easiest ways to do something like that is by taking a little area of the image and choosing the maximum value there. Right? So we could take a little area of an image, look at all the numbers, choose the maximum value, and then produce another smaller image that maybe has these features highlighted a bit more. And this process is called max pooling. And so depending on your example, you might want to max pool, you might want to min pool, but basically you're doing this. So the output from the convolutional step produces another matrix. So up here we see this matrix, maybe these are the output values of that convolution. And now what we're going to do is we're going to take sub-areas of this image and we're going to produce the maximum. We're going to produce another area which are the maximums from each of those areas. So for example here, this forms another matrix which is probably going to be smaller since you're taking these sub-areas. And this is called pooling. And so what you've done here is you've looked at this part of the image and you've sorted, I'm going to only remember the most important feature from that part of the image, right? I'm only going to remember the most important feature from this part of the image. And so what this does is you get some images over here, or you get some values over here in your matrix. You have some sort of thing called the stride, which is how far over this pooling goes. You get your patch size, which is, okay, in this case it's 2 by 2, and then you produce another matrix over on the side, which doesn't stay on the screen for very long, but this is our pooling output over here. And then, depending on, again, the size of the problem, the nature of the problem, you may repeat this process a number of times. And so the convolution to max pooling is repeated some number of times. I don't know why I said 100 there. That's way too many. Maybe I meant to say 10, but I'm just going to delete that number there. Oops. Hang on, I lost my spot. So this process is repeated some number of times, and then we can optionally run the result of that output through another convolution, and then another pooling, and then finally, the output is run through a fully connected neural network. How many times do you do that? I don't know. It's depending on the problem. Some people do it a couple of times, maybe once, maybe a dozen. Try different architectures in your deep neural network and see which one produces the best results. So what we get is a neural net that kind of has this sort of architecture, where we have our input image, we have that first convolutional layer that we talked about, then we have some pooling layer that was max pool or min pool of those features, depending on what the feature was. Then we take those features, and we may run that through a convolutional layer, and then another pooling layer. And now what we do is once we have that, okay, these are the features that we're really interested in, and we're going to run those features through our fully connected neural network in order to learn something about that neural network. Another important step here is the activation function. We talked about the activation function. Yep.
So what's the difference between a deep neural network and a convolutional neural network?
So yes. So a convolutional neural network is just a neural network that uses convolutions to pre-select features, right? A deep neural network is just a deep neural network. It has a lot of layers. So this over here, this fully connected network, like this may have dozens and dozens of layers, right? It's just really big. Deep neural net means really big neural net, but typically they do have these complex architectures that go from the input through feature selection to network, which may or may not be fully connected. And like the architectures for these networks could take up slides and slides and slides, right? This is just sort of the overall view. So yes, that's a really good question. A convolutional neural net here, this is actually probably not a deep neural net if we only have one fully connected layer. But deep neural network is this sort of hand-wavy term. It's a normal neural net up until 3 layers, and then it's a deep neural net. No, deep neural net is just sort of like a marketing buzz term that people like to use because it's bigger, right? Instead of having 2,000 weights in a neural network, we have 1 billion weights in our deep neural network or something like that. Okay. Something else that's done to these convolutional layers sometimes, most of the time nowadays, is this activation function called a rectified linear unit, or ReLU. And essentially what ReLU does is it takes all this says for this ReLU, and this is a simplification of ReLU. There's other variants of it that are a little bit more complicated, but it says, I'm going to take all the negative values and turn them into zeros. And then all the positive values are just going to be their value. So it just turns all the negative values black in the image. That's it. And so what that looks like is we may have this as the result of our input feature from the convolution, and then we apply ReLU, and we get this sort of another way of like adding more contrast to the image. So in this example of our car, we take our car, we put it through a convolutional layer up here. Then we put it through ReLU, this activation function, to get a higher contrast image. And then we put it through some pooling layers to get this even higher contrast image, right? So deep neural networks, even though they're great, if you just feed in the image without doing these convolutions, it's actually quite difficult to learn about features. So even though deep neural nets are the new hotness and they're supposed to be able to learn anything, there is sort of this handcrafting feature layer of convolutions happening beforehand in most cases, because it just helps us out. It simplifies the problem. It makes it easier for the deep neural net to do the learning, and so why wouldn't we do something like that? So what we may get in the end is something that looks like this. This is quite small, but we get in the first layer, we may get, how in the neural network layer, I talked about how the first layer are like features on the input, and then the second layer are sort of features within the first layer of features, and then the next layer is like features of the features of the features. And so in the first layer, maybe we get these are just edge detections. In the second layer, we get combinations of edges. The third layer, we get combinations of edges. And eventually, we get this layer that's actually to be able to detect, there may be a car in this image. And this, again, is a gross simplification. We can see here that this is just more examples of what we've seen already, which are example architectures of deep neural nets with convolution. So we take an image, convolve it, pool it, convolve it, pool it, convolve it, pool it, and then some number of fully connected networks. And then the outputs of this network, let's say we're doing classification of animals or features or whatever, we would have one output for each possible category, and then we would be assigning a number to each of those outputs, which is our sort of belief in how likely it is to be that thing. So here, for example, to us, we can tell that there's a boat in that image, and so over here, the output of this neural net is like, well, there's a 2% it's a bird, a 94% chance it's a boat, a 4% chance it's a cat, and a 0% chance it's a dog, right? So that would be the output of this neural network. And again, just another example of this. So back in 1998, Yann LeCun, who's, at least the last time I checked, still the head of Facebook AI research, was basically like the grandfather of convolutional neural networks. And this has been going on for a long time. It's not just in 2012, everything started happening. So especially for character recognition, for writing recognition, so in 1998, this was the architecture that Yann LeCun had, and they didn't have all these big, massive GPUs for parallel computation back in the day. So the number of transistors that they had in the CPUs back then were like 10 to the power of 6, so a few 100,000, and the number of pixels used in the training set were like a few megabytes of images, for example. And now we have, in 2012, GPUs have so like billions and billions of transistors. We can do lots of things in parallel, and then we use like petabytes of data in the training step. So it's just in the course of 20 years, the amount of processing that went into neural nets just absolutely blew up. And it turns out that like Yann LeCun's stuff with neural nets is kind of like as far as they got until someone said, let's throw massive amounts of computing at this. And it turns out that convolutions, pooling, and lots of computing was really the difference between neural nets like almost being cut from AI classes to being like as popular as they are today. Yep.
So for something like the 2012 results, how do you determine the sizes and the order and the types of things that are going in? Is it trial and error? Is it just looking for better options and slowly iterating? Is there a mathematical basis behind it?
Well, I would have to assume that the first time you do something, there's a lot of trial and error. But it's guesstimation, right? It's educated guessing. They're not just literally trying random things. They're saying, okay, edges are cool. Let's put an edge convolution in there. It would be cool if those features were a little bit more enhanced. Let's try a bunch of different techniques, right? So this is definitely not the first thing that was tried, right? There was 2 decades of research in between here, or 15 years, or whatever you see. So I've seen people working on neural nets that know very little about theory. They're given most of these like TensorFlow type APIs that you have now. You can literally drag and drop like you're programming in Scratch. I want another max pool layer. I want another convolutional layer. Here's the kernel. I want another max pool layer. And so you can literally just drag and drop and try all possible permutations of these things and see if it works. There's a little bit more to it that's going on, right? There's theory that I don't know because I'm not my field of research is not deep neural nets. But people have found for this type of problem, this thing works really well. For this type of problem, this thing works really well. This type of activation function works really well. So if you were going to do this, what you would do is see what other people have done in the past and do a similar architecture. But yeah, a lot of research in the beginning is just playing around to see what works. And again, another example that I don't really have to go over, which shows like in this example that NVIDIA did, convolution, ReLU to get rid of those negatives, another convolution, another ReLU, now we're going to pool. And so like in this example, it wasn't conv pool, it was conv ReLU pool, right? So it's just, I don't know, like what is there was that meme where it's like, you can't just try a bunch of random stuff in hopes that it works, and then the second panel is like, oh, that's called machine learning, right? So, yeah, you can put all these different techniques in different orders and see which one produces the best result. And these are just different. So what this is a sort of visualization of the importance of the features in these neural nets, right? So as you learn the weights. Did anyone actually watch the neural net lecture and then pull up the TensorFlow example and then actually try it? Hey, we got one person who did it. Great. I recommend doing that before the exam. Pull up that TensorFlow playground that I linked in that lecture and actually do the examples that I did, because I think it will help you understand a bit more, because you actually get to see the weights change over time and like your outputs change. It's really neat. And if I had done it in person in class, which I wanted to, but I wasn't feeling well, I would have actually gotten you to pull out the laptops and do it in person. And so these techniques are only recently, I say recently because I made these slides 7 years ago, but in the last decade or so, our ability to do these neural nets in parallel has just exploded. GPUs have become ubiquitous, very cheap to manufacture, and then you're trading, essentially with GPUs, you're trading single processor speed for massive parallelism. And neural nets are inherently parallel. So over here, you've got like a modern CPU architecture where you have multiple cores in your CPU. Then they share some cache, and then you have system memory, versus over on a GPU, you have your whole device memory, and then you have a bunch of CPUs, or a bunch of GPUs over here. So these processors are probably between 1/10 and 1/5 the speed of a CPU core, but there's so many more of them that the total processing power is way higher. And so I just have a little video here. I hope this doesn't deafen anybody. I'll see what the sound is like, and then I'll try and turn it down.
All right, I introduced to you Leonardo. And we hit this trigger on this thing. 2,100 gallons of air goes through these accumulators, out these valves, into all
exactly
1,100 of these tubes, into these tubes in which the bottom of is a paintball. Each of those paintballs will fly across 7 feet of space and in 80 milliseconds reach its target. Hopefully, when it's all said and done, it's going to paint the Mona Lisa.
GPU painting demonstration.
Yep.
In 10,
9, 8,
7, 6, 5, 4, 3, 2, 1.
So I like that example. It's obviously contrived like marketing by NVIDIA, but it does illustrate the power of parallelizing computations in neural networks. And if I just look at a standard fully connected neural network, each one of all the dot products that we have to do, so the weights times the inputs, and then summing those all up, they can all be done in parallel for an entire layer. So we can do all of those in parallel for this layer, and then they produce the inputs for this layer, and so we can do all of these in parallel. So we've got no shortage of things that we can do in parallel for a neural net to let us do that GPU. Another thing that's become very popular recently and very powerful is the idea of autoencoding. I'm not going to go into all the mathematics of autoencoding. I just want you to kind of know what an autoencoder is. So it's a hidden layer, which is, I've got inputs, so x1 to xn, so standard inputs for a layer. And then we've got a hidden layer, which is smaller than the input layer. Then I've got an output layer, which is the size of the input layer. Interesting. And so our target values are the input values. And so what this does is it ends up finding generalizations of patterns on the input. So if I have an input layer of an image, for example, and what I'm trying to learn is the image, what good does that do? Well, the point here is that we're passing it through a smaller hidden layer. So if we take data and we're passing it through data that's smaller, and then we get back to the original data somehow, what's the term that we would use for that in everyday computing? You've all done this, trust me. Not quite. Compression, right? You're taking data, making it smaller, and then making it bigger again. And so it turns out that this sort of autoencoding, when we compress data it learns something about the important features of that data, right? If we're able to compress something, it means we've learned something about the patterns in that data. If we didn't know anything about any of the patterns in that data, then we couldn't possibly make it smaller and get back to the original data. And so autoencoding generalizes inputs, and you can see it as a form of compression. And DNNs can use autoencoders as well. And so the idea here is that we have some input image. It goes through whatever. Maybe it goes through features, maybe it doesn't. And then the layers are gradually and gradually shrinking until we get to this. It's called a latent space representation. And this is where it sort of learns those features that are present in that image. And then it grows back to the reconstructed image that we had. So for example, this process goes through two things. So the input goes through the shrinking layers, which is called encoding. And then that latent space or encoded representation is the smallest layer in the middle. And then we have a process of decoding. And you've all seen JPEG compression. I'm not saying JPEGs use this structure. This is a neural network. But this process of encoding and then decoding the image, typically, we get something that is recognizable out the other end, but it may have encoding artifacts. It might be blurry, grainy, some spots on it or something like that. So here's just a cool animation that I saw of an autoencoding working on this MNSIT, like the integer data set that's very popular for training neural nets. And what we see down here is that through these different layers, we learn the features of these and eventually do get out, like, this is the input layer, this is the output layer, this is sort of the compressed layer. And so what we're doing is we're learning the features of these things through smaller and smaller layers. And if you had gone through the neural network lecture and done those examples, you would know that, hey, if we have fewer neurons to represent things, then it's easier to do the learning, right? So the only reason that we want to use big neural nets is because we have to have enough ability to recognize features in our particular problem. But if we could get away with using a single neuron, we would obviously want to do that, right? A single layer, single neuron, that's the dream. Because it's so much less, how do you say that? It's a lot less things to learn, so it takes a lot less computation and a lot less time if we can get away with using fewer things. So that's sort of one of the motivations for this autoencoding process, is that if we can shrink our problem as much as possible, then we would want to do that before we actually try and get the neural net to learn about it. And sometimes this fails, right? So sometimes you do it, sometimes you get something good out. Oh, this is one of the examples where it fails. Over here, this is what the encoder thinks the Pokemon look like. So it's not always perfect. But we do typically see, if you pass data through a smaller channel and then reconstruct the input data, it's typically going to have some artifacting, right? But ideally, it's still to the point where you can recognize the thing in the image. Now, there are some things that you can do in the training phase of neural networks in general. So these are not only, the next two things I'm about to show you, dropout and drop connect, are not only done in neural nets, but also, not only done in deep neural nets, but also regular neural networks. And they just help you a little bit with training. So the curse of the neural net, as we also saw with genetic algorithms, is that they can get stuck in local maxima. And so dropout is a technique that we can apply that says if on every iteration we flip a coin for each neuron, and depending on the output, we can disable the neuron. On the next iteration, you drop out a different set, etc. And what this can do is it can make your neural nets a little bit more robust to changes in input. Jeez, excuse me. And it can also help it to prevent getting stuck in local maxima. So essentially, if we just had what dropout is, all of the inputs go to all the neurons of the next layer, and then all of their outputs go as inputs to the next layer. But in dropout, what we can do is for each neuron, we can actually flip a coin, disable neurons, etc. And the point here being that, like, if you go into your brain and you cut out a little piece of it, right, you're not going to just, well, okay. Sometimes when that happens, people have brain injuries where they don't forget everything that they knew, right? The brain is kind of robust in that way. Now, you don't want to put too many holes in your brain, but you can see this as sort of putting little holes in the brain, little neurons being turned off. And the idea here is that if we can still learn something with these neurons turning on or off, then we've got a pretty robust neural network. And then what drop connect is this is sort of the general case where instead of turning on or off entire neurons, we can just turn on or off specific connections. Okay, so these techniques are sometimes used. I'm not going to ask about that on an exam. This is just so, hey, if you're ever reading something and they say we use drop connect with a probability of alpha or whatever, you'll know what those terms are. And so what is deep learning then, now that we know what a deep neural net is? So typically in machine learning, we take our data, maybe we extract some features from it, and then we do some classification. Maybe you have a support vector machine or a tree or a forest or whatever, and then we have some output for our classification. Well, deep learning is just using a deep neural net to do those intermediary steps, right? So that's all that it is. It's machine learning using a deep neural network. Deep reinforcement learning, what is that? Well, we have in this course, all of our reinforcement learning was tabular reinforcement learning. And what tabular reinforcement learning is that, hey, our problem space is so small that I can have an array with a bucket in the array or an index of the array for each possible state, right? But tabular reinforcement only goes so far. We can only have discrete state representations and really low dimensional data and really low state spaces. So we require function approximation, right? We require this QSA. Like, we need to be able to store the action values somehow. And so, in general, this QSA could be a generalized function. It doesn't have to be a table, right? And so, it doesn't have to be a table lookup. And hey, deep neural nets are really good at function approximation. And so, what deep reinforcement learning is essentially what we've done with reinforcement learning, but instead of having a table, we have a neural network to store those state action values for us, or the policy for us. So if we take our table, turn it into a deep neural network, we have deep reinforcement learning. Deep Q networks were the first published form of deep reinforcement learning that I know of. And they use a deep convolutional neural network for function approximation to approximate the optimal state action value function of Q. And so it uses a modified version of Q-learning that changes when updates are performed. And the paper, if you want to go read it, here's the PDF for you. It's called Human Level Control Through Deep Reinforcement Learning. And that was the paper that did the Atari learning. So they learned to play Atari games with deep reinforcement learning. And so Q-learning over here, we have our states and actions. We can just look these up in a table because our assignment 5, for example, is so small that there's only a few states, so we can fit an array of that size. But think of what we would have to do if we wanted to learn about Go or chess or checkers, where we can't store every possible state of the game in a table. Well, enter the neural net, right? So the neural net is an approximation formula, or it's a function approximator that approximates that QSA for us. And then, if we did look at that paper, I'm not going to read out this whole thing. I just wanted you to see this formula. Now you can start to understand this math. Look at this formula. R plus gamma max A QSA. This omega here has to do with the gradient descent. This is the error in the gradient descent, I believe. Minus Q of SA. That's crazy. That's basically what you did in assignment 5, but it's a deep neural net now instead of a table. Okay, so as you learn more and more about this, the math of these papers will become more and more obvious. At least to me, I look at this in terms of like a for loop instead of the math, right? Because I'm bad with the math. So what they did in that paper was the inputs were the states of the game, the actual pixels of the Atari screen, ran them through some convolutions, then through a fully connected network, and what they did was directly learn the policy. So they didn't learn the QSA values, they just directly learned the policy that led to the best reward. And so the outputs were one output for each possible combination of the Atari inputs. So there's 8 directions that you can press on the joystick and a button on or off. So for each of those 8 possible directions, they also had it, or 9, I guess, because there's a neutral position as well. So there's only pressing the button and only releasing the button. There's pressing left with the button, pressing left without the button, and all 18 or 20 of those combinations. So that's what they did in their paper. Then what AlphaGo did, which you will learn a bit more about when you watch the video, is that they combined deep learning with heuristic search. It's a form of heuristic search called Monte Carlo tree search, which we didn't go into in this course. I didn't want the whole course to be about search, but Monte Carlo tree search is essentially a depth-first search, but instead of using, I don't want to say it's a depth-first search, it's a search that doesn't use evaluations. So think of alpha-beta search, but instead of evaluating, what they do is, instead of applying an evaluation function, they say, okay, evaluation functions are good, but they're not very accurate. So what we'll do is instead of evaluating from here, we're going to do a random playout of the game. So we're going to take the game state where it is, and we're going to play a game to the end of the game by performing random actions. So I'm going to place a piece here, I'm going to place a piece there, place a piece there. And the idea being, as you search more and more and more, if I'm at a particular game state, and I play to the end of that game 100 times using random actions, and 90 of those times in Connect 4, the red player won, and the yellow player lost, then if I did random actions, and the red player won 90% of the time, it's probably the case that that state is better for the red player. So it's one way of doing an evaluation of a state without actually having to come up with some numerical formula or whatever. And so in AlphaGo, they learned 2 networks. One was called the value network. So given a particular state, how good is it to be me in this state? So a value of 1 would mean that you are always going to win from that state. A value of -1 means I'm always going to lose from that state. And then they learned a policy network, which was, given a particular state, what is the goodness of me doing these actions? What should I do here? So what they ended up doing was saying, I'm learning a value network. Think about alpha beta. The value network is the evaluation function. So we've learned by deep reinforcement learning and heuristic search, a value network, that's my evaluation function. It's a really accurate evaluation function because I've learned it. I haven't just tried to come up with it in my head. And then the policy network, what move should I do at S? Well, if the policy network can tell us like the top 3 to 5 moves that I should do at a specific layer, then in my alpha beta, instead of looking over all possible 200 moves, I only need to look at like these 3 or 4 or 5 moves, right? Someone is clicking a mouse multiple times per second, and it's very distracting. Thank you. It's okay. It's a loud mouse. I normally don't mind, but it was really fast. So this was used to enhance the Monte Carlo tree search. We've learned an evaluation function, and we've learned at which moves we should look at in our search. So that's really, really cool. So what the first version of AlphaGo did was learn from human replays. Right? Sometimes it's very difficult to just start from scratch and start learning. So DeepMind had hundreds of thousands, if not millions, of professional human Go games that it could learn from. And so what it did was it learned a policy network. If the input is the state and the target is the move that the expert human performed at that state, it could do this sort of imitation learning, where it learned a network that mimics what a human would try to do at those states. And then what it did was it learned a value network where the input was the state, and the target was, hey, if we have this state, who ended up winning the human game from this state? And so it learned how good it was to be the white or black stones at that particular state. And so once it had learned from the humans, well, now it's kind of, pretty good, and so then it started playing against itself. And there's this sort of positive feedback loop that happens. Once you get pretty strong, you can play against yourself to get even stronger, and then you're stronger, so you can play against yourself to get stronger. right? Imagine you're playing Smash Bros. And you can just play against yourself all day. And okay, now I'm better, so now I'm playing against someone better. And then they're better, so now I'm playing against someone better, right? So computers can play against themselves. It's really cool. Also, I mentioned before, the bad part about learning is that you can only learn about what you've visited. And so if all you do is learn from games with expert humans, maybe you don't get to some of the, if AlphaGo played against me, I'd do some crazy move that was really terrible, and maybe it didn't know what to do in response to that because it's never seen it before, right? Yep.
So when it was learning from itself, wouldn't it just do the same moves over and over?
Well, this is the thing down here, right? So no, because the neural nets and the training process, there is a little bit of randomness in there. And also key is to throw in some random moves to learn about states that you don't visit. So remember we talked about exploring starts and randomizing actions, epsilon greedy. All this stuff is in the training phase as well, right? So they do randomize actions and stuff to make sure that they're not just doing the same thing. And then AlphaGo 0 came out. So after the movie AlphaGo, that only talked about the first version of AlphaGo, then they made AlphaGo 0 that learned entirely from self-play, like really, really huge leaps and bounds in terms of reinforcement learning. So it still used search, it still used Monte Carlo tree search to play games against itself, learned which moves were good from self-play by using deep reinforcement learning, and it converged faster and used less computation than the original AlphaGo, and it ended up working in chess as well. So up here, we see this is from the actual paper for AlphaGo, and this is self-play reinforcement learning in AlphaGo. And up here, it uses Monte Carlo tree search to guide the playthroughs in that tree. So you still have to do exploration versus exploitation in this learning, and the Monte Carlo tree search was helping with that process. And then here, this is, Monte Carlo tree search in AlphaGo, or in AlphaGo 0, so even Alpha 0 did use search. So people are going to tell you, oh yeah, but all the best things are now, look at AlphaStar, look at AlphaGo, it's all machine learning. But there's still search techniques in here guiding the learning, right? That exploration versus exploitation is still being done. And so really, it's a combination of both of those techniques, deep learning and heuristic search. So heuristic search, Go has a huge branching factor. I kind of already talked about this. I forgot I had a slide on it. Humans have good abstractions of what moves to perform at a given state. Garry Kasparov, who was the world chess champion for many, many years, famously said that he only ever considers 2 of the 50 moves on a chessboard, right? Because he can just look at a chessboard and instantly tell you, these 2 moves are the only 2 moves that you should do. And then does that search, alpha-beta search in his head, to go down 20 levels deep to see that. AlphaGo learned a policy network. And so when it learned the policy network, now it can narrow the heuristic search to only consider the moves that the policy network says to do. And so search also needs a good heuristic function to determine how good a state is, and that was the value network. Another program, which we don't have a movie about, unfortunately, was called DeepStack. And so this was taken at the University of Alberta. This is Michael Bowling, who's one of the professors there. And this was happening while I was doing my PhD at the U of A, so I know most of those people. And they did the same sort of techniques, but for playing poker instead of for playing Go. And so what they had was the input state were the cards. Now they also had this, this is called deep counterfactual value networks. They used a technique called counterfactual regret minimization. And what that does, it's a game theoretical algorithm, because you don't know, when you're playing poker, for example, you don't know the best move to do, right? Unlike chess, because you don't know what's in your opponent's hand. There's some uncertainty there. So what they do is they play out a card, and this is a gross oversimplification, but you play out a hand of cards, and then after the hand of cards is over, you look at what the opponent had and say, now that I did what I did, how much do I regret it based on what they actually had? And then you say, okay, I regretted that a lot, so maybe I should change it and then update the value. So it's a different type of learning algorithm that I'm not going to go into. But the point being here, there was that algorithm, there was a little bit of search, and then there was deep reinforcement learning used to be the evaluator. Okay, I'm in this particular state, there's this many chips on the table, I have these cards in my hand, these cards are on the table, how good or bad is it to be at this particular state? So similar techniques. Most of the big things that have happened in game AI have come from combining. So back 20 years ago, it was almost entirely heuristic search like alpha beta. 15 to 10 years ago, it was Monte Carlo tree search. And now 10 to present years ago, it's deep reinforcement learning combined with Monte Carlo tree search. Okay, the last thing I want to talk about yet is even though deep reinforcement learning or deep learning is really, really good, convolutional neural networks are really, really powerful, they're still not human, and in some ways that's good and in some ways that's bad. So what do deep neural nets see? Okay, so here is one image, and here is another image. Now, what is happening inside a neural network? We are taking values, multiplying them with weights, and summing them together, right? You can think about an image like this. If we change specific values to like, oh, I'll change this 5 to a 3, or this 200 to a 100, what the image is may not change, right? But what the output of the neural network is may change. So what some people do is they do these sort of papers on tricking deep neural networks. So what they do here is they take an input image, and then they learn what values to change to produce an image that looks almost identical, but produces an entirely different result from the classifier. So these inputs of this is a school bus, this is some sort of bird here, which is kind of hard to see, and this is some sort of temple or pyramid. They've learned to distort it with this noise so that the same deep neural net that previously thought it was, like, it correctly classified it, now thinks these are all ostriches. So if you run these images through the neural net, even though to us it looks the same, because there's like the changes are sort of randomized noise, now the neural net thinks, oh, that's an ostrich, oh, that's an ostrich, that's definitely an ostrich, right? Over here, again, more examples, oh, yeah, that's an ostrich, and that's an ostrich, and that's an ostrich. So the neural net thinks that's an ostrich, but that's a dog. It thinks that's an ostrich, but that's a pyramid, right? Now, you can go back and forth with this, where you take a trained network, then you train another network to trick the network, and then you go back from that and you retrain the neural network. And so there's like, this is not exactly what it is, but there's things called GANs, adversarial networks, where they try and beat each other, and through the process of trying to beat each other, they get something much better in the end. But just to let you know that, like, you know, hey, this is a robin. With 100% accuracy, this is a cheetah, right? This is, with 100% accuracy, an armadillo. This is an electric guitar. This is a baseball. Actually, I kind of see a baseball there. But like, you can modify the inputs in a way that the outputs of the neural nets are fooled. So deep neural nets are an amazing feat of engineering and mathematics. They produce spectacular results, but they're not magic. They are mathematics, and the mathematics can be tricked. Okay, so you can always produce inputs in a neural net that can produce outputs. And the tricky thing about this is that it goes from, oh, okay, maybe academically speaking in your project, you got, you know, a lower grade, boo-hoo, who cares that you tricked the neural net. But the really bad thing is, you know, you've got Teslas thinking that grandma is a baseball, right, if some hacker decides to do something like this. So it's kind of an interesting philosophical question on whether we should like rely on math that could be tricked and stuff like that. But anyway, that's all I really had to say about that. Now you know what deep learning and deep neural nets are. And what I'm going to do really quickly, while I still have some time, is go over the final exam info that I posted. And so the final exam for the course is on Monday, December 11th. Everyone can confirm that that's what they've seen. Just want to be sure. Saw a lot of heads nodding. That's good. In this room, from 9 to 11 a.m. I'm sorry, I certainly did not schedule that. I hate 9 a.m. more than all of you combined. I can guarantee that. So the exam will be the same format as the midterm and contain approximately 50% more questions. So instead of being 4 pages of questions, it will be 6 pages of questions, but you'll approximately have double the amount of time, so it'll be fine. It will cover all the material presented in the course, including assignments and supplemental videos, Matchbox Learning, AlphaGo movie, and the neural net implementation video. About 80% of the exam will be from the second half of the course. So if you only study the second half and you get less than 80, I'm sorry, but just, study everything. So lecture 11 and onwards, 80% will come from that. If we set it in class, appeared on a slide, or done during an assignment, it can be a question on the final. The questions on the final will not be harder than the questions on the midterm. It will just be different subject material. So you've all got a taste for what my exams look like now. Yeah?
I don't know if you can answer it, but are you supposed to learn the mathematical formulas that you gave in class?
So read what I have highlighted.
Yeah.
Yeah.
Okay.
Yeah, unless I've specifically told you not. There's not a lot of, okay. If I showed that like DQN formula from the AlphaGo, not that, right? Where I specifically did examples, right? So I'll go over some of the slides in a second to sort of answer that question. No questions will be exactly the same as the midterm. Pay specific attention to all formulas and examples from the lectures where we did example calculations. That's the important part. If I did a calculation, that calculation with different numbers could appear on the final. Any computations on the exam will not require a calculator. Most will be simple fractions or integer numbers. So if I go through, like for example, from this lecture, I could ask like what a convolutional kernel is, like the definition of anything here, right? So basically this, I'm not going to get you to do convolutional examples, like numerical examples, but any of the definitions here, anything of what AlphaGo did, that could be a question from this lecture. Let's save the changes to that. Let's see. So what did we do? We did evolutionary computing and genetic algorithms. So, these sort of definitions, you don't need to know the history of stuff. None of the biology stuff is going to be on the exam. This is important, right? The actual process of evolutionary algorithms. This could be important. So what are the different types of evolutionary algorithm? Genotype versus phenotype representation, that's important. You should know that. Fitness functions, what they are, why they work. Go look at assignment 4, what you did for assignment 4. The graph in assignment 4, like why did certain numbers go up? Why did certain numbers go down? Roulette wheel selection, we did that. Okay, so that's pretty much that lecture. All of the definitions for reinforcement learning are important. There's not many of them really. Like returns, value functions, policy, at some point I give you what are the elements of reinforcement learning problems. Those are important. Similarly for an MDP, what do all those values mean? Bandit algorithm, we did a calculation. Remember this one? I could give you that on the exam, so I would give you example inputs. You calculate the QSAs. I'm not going to get you to derive any of these formulas. All the incremental update stuff, what does alpha mean? Epsilon greedy calculations, so the epsilon soft stuff, which I know is not in this particular set of slides, but if epsilon is this, and here are the values, calculate the greedy ones, what's the probability a greedy action is selected, what's the probability of this, what is the epsilon soft policy that is output by this thing. Here, this example of like, okay, having a higher epsilon, you learn faster, but you're still choosing random actions more. So over time, if you have a longer training period, the lower values of epsilon may be better. These algorithms, the bandit algorithms, QSA versus VS, that's an important thing. MDPs. I don't think I'm going to ask anything about discounting because like it's just a value. What I'm going to ask. Yep.
Should we expect pseudocode for the first half of 4.5?
It can appear there. All I'm saying is that 80% of the grade or content of the exam is probably on the second half of the course, 75 to 80%. No question will be exactly the same as the midterm. But that might mean that I get you to write minimax instead of max value, right? So it's, I will not get you to write the full algorithm of alpha beta. There's a weight off your shoulders I get. Episodic versus continuing tasks. Markov property, what is that? I might give you an example environment. Is it Markov or not? A dynamic programming example. This example is important. Policy update. Most of these algorithms are like the same, right? They're just like minor differences in them. Value policy iteration. Monte Carlo. I mean, I'm not going to ask you to draw a bunch of random dots. VS versus QSA, that's important. If I gave you this, doing a value update, just know how that example works. Here's I gave you the state sequence, the action sequence, the reward sequence. First visit versus every visit MC, what does that mean? Where can we use the differences between dynamic programming, Monte Carlo, GPI? Of course, at the end of some of these lectures, there's sample example questions. You can look at those. Temporal difference learning. Just basically, this is an important slide, right? Like, what's the differences between MC, or what parts of MC and DP does TD learning do? The cliff example is a good example. Make sure you understand that one. Might be a question about that. SARSA versus Q learning. Hey, why is SARSA better in online? Why is it better in training than Q learning? So there's some exam questions there. Neural nets. Jesus. Threshold logic units, and these things here, know about those. Like this calculation is pretty easy. Might give you one of those. I'm not going to give you one like this. It's the same calculation, it's just more numbers. Linear separability, what is that? What is a neural net? What is a neuron? Know the diagram of a neuron, the different parts. Might get you to label a diagram or something like that. I'm not going to ask any questions about gradient descent. I don't want to get into calculus or grading that. Activation functions, why are they important? Here's a good neuron example. If I ask you anything about a neuron on the exam, it's this artificial neuron, not the biological neuron. Did you have a question? I was going to ask. Okay. Yeah, no biology, none. I might ask you like something about evolutionary algorithm. Obviously, some evolution is there, but none of the actual biological parts. The types of networks that AlphaGo trained and why they are important, how they helped the learning, how they helped the search. We just talked about that. Explain and compute the output for a TPU, explain linear separability, compute whether or not a simple function is linearly separable, describe the structure of a neuron or neural network, implementation of neural net and AlphaGo videos. Will not ask any gradient descent. That's pretty much all I have, unless there's any specific questions. I still have my office hour today, if you need help with anything. Yep.
For the evolutionary algorithm slide, you said that you have to know the difference between phenotype and genotype representation. So yeah, the slide that you referred to, it just had an example of
Yep.
So what should we know? Like, are you going to ask?
In an evolutionary, well, I'm not going to say what I'm going to ask, but know the difference between a phenotype and a genotype. Yeah.
There's no definition of phenotype or genotype. Right?
Yes, there are. Yeah. So the genotype is the gene. So that's what we do the actual calculation with. The phenotype is the representation in the environment of the actualization of that gene. So our DNA genotype, the fact that I'm strong, phenotype. Yeah. Very strong. Yeah.
If you got us, for example, to define the value function,
Yep.
would it be okay to either give like the mathematical definition or explain?
I'll be explicit about what I want. Yeah. Yeah. Bellman equation. Yeah. Anything else? I mean, there's 2 weeks till the final, so any questions you have, just feel free to email me as well. Okay, thanks. That's it.